We're asked to look at this truss, which is made up of members 1, 2, and 3. The truss is supported by a pin joint at A. It's supported by a roller connection there at B. There's a horizontal force there at C. We want to first determine the loads, that is, the forces that are carried by members 1, 2, and 3. And 2, we want to look at the minimum size of this pin D that holds together the two subsections of 1. And we want to size that in a way that with a factor of safety of Fs, that this pin will not fail in shear in yielding. So again, we want to have a factor of safety against that failure. So the first thing I'm going to do is look at equilibrium. And equilibrium here means I'm going to be looking at method of joints for joint C and joint B. The forces that I have acting on joint C is the applied force P. There is a force there, load F1. There's a load of F3. F3. There's going to be a load exerted by member 2 on that pin, and there's going to be a roller support here, so there's going to be By. So we can deal with trig. This angle phi. We'll say that phi is going to be given to us in terms of the dimensions of the problem. So that's going to be inverse tan of opposite, which is h, divided by adjacent, which is b. So that's known information. And how about this one here, theta? And theta is going to be also given by an inverse tan of h, in this case, over a. So again, these two angles we know from given information. This angle is theta. This angle is phi. Likewise for here. X is going to be positive to the right, Y is going to be positive up. So if I look at pin C, if I sum forces, let's see, in Y first. Summing forces in Y, I get minus F1 sine theta minus F3 sine of phi. For equilibrium, that is a 0. So I get that F1, I'm sorry, let's make that F3. F3 is equal to a minus sine theta divided by sine phi times F1. Summing forces in X, I get minus F2, oops, I've jumped down to the wrong FBD. Let's stay with C here. Summing forces in X, I got P minus F1 cosine theta plus F3 cosine phi. For equilibrium, that resultant is a 0. So what I'm going to have here is minus cosine theta minus sine theta cotangent phi times F1, and that's going to be equal to a minus P. Making sure that I've got everything correct here. So it says then that the load carried by member 1 is going to be P divided by this trigonometric expression here, cosine theta plus sine theta cotangent phi. So this gives us the load carried by F1. If I move, also, therefore, from above, then F3 then is going to be minus sine theta divided by sine phi times F1, so that's times P divided by cosine theta plus sine theta cotangent phi, like that. So this will be F3. For what it's worth, F3 is in compression where F1 is in tension. From our free body diagram of B, when I sum forces in X, I'm going to get minus F2 minus F3 cosine phi, and therefore from this I get that F2 is going to be equal to minus F3 cosine phi, so that's going to be a plus sine theta cotangent phi P divided by cosine theta plus sine theta cotangent phi. And so this answer here is for F2, it's a plus sign, so it means that that is in tension. Okay, so that gives us our loads carried by the members 1, 2, and 3. Now we want to come up and look at the pin, this pin right here. And let me just make a sketch here. If I look at this pin, what we're going to have is on this side we're going to have a double-sided connection. On this side we have a single. So this is going to be equal to F1, and then each one of these is half of that, F1. So what dictates the shear stress in the pin is the 1/2. That is, our shear stress is dictated by this because it's supported by 2 points. So when I scroll down here, what I'm going to say is that the shear stress in the pin is going to be the shear force divided by pi r squared, so that's pi times d over 2 squared. V in this case is F1 divided by 2. That gets multiplied by 4 coming from the bottom there, pi d squared, like that. So that's the shear stress we have in the pin. Let's take it one more step. That's 2F1 divided by pi d squared. We know that from our factor of safety equation that that's going to be the shear stress that we're going to design against. So that's tau yielding compared to the stress that we actually have, tau pin. So that's equal to tau yielding divided by 2F1 divided by pi d squared. So let me take a couple more steps here. Pi tau y d squared divided by 2F1. So the minimum d that we'll have for that factor of safety that's given is going to be 2 times F1. We know that, divided by our times factor of safety, divided by pi tau y with a square root in front. So that's the minimum diameter pin that we can have. The first part of this is very basic stuff, what you have done before in other courses. Find the load carried by each member in the truss. I use the method of joints. But here we're given that Member one is actually two members that are spliced together, held together with this pin, and it's a double-sided connection. So the load that's carried by that member there, F1, half of it goes on one side and half of it goes on the other, and that half is what dictates the shear stress in that pin. And so that's from where we get this. And then lastly, for our design, we want to use a given factor of safety to back out what minimum diameter pin that we can have and still have that factor of safety.